Hello, good day. My name is Dr. G.S. Javed. I am from Intel and I will be presenting our paper along with our co-authors Miryala Chandrasekhar and Komal Deshmukh on the topic a 0.009 mm square, 0 to 230 milliampere wide range load current output for a capacitorless low dropout oscillator for high bandwidth memory parallel IOs. It's a long title. Let's go forward. A quick overview of our topic. We will go ahead with a brief overview of the LDO and its operation. We will focus in detail about the design challenges in having a 230 milliampere current load delivery. We will look at the layout challenges, go deep dive into reliability and power delivery, followed with the results, and we will conclude the talk. An LDO is basically a regulated voltage output for a defined maximum load current. What you have is you have a PMOS transistor in a negative feedback circuit with an error amplifier which takes an input from a reference and gives the output according to what is the analog circuit voltage that is present and what is the amount of current drawn. Here we have a resistive feedback network which compares the two reference voltages that are present here, and the load current is modeled as a capacitive output along with some amount of resistance. The pass transistor here is a PMOS pass transistor and it has its gate connected to the voltage supply using a decoupling capacitor. So what are the unique challenges that we see in 230 milliampere load delivery? First thing, it's the simple large load current which is present. This large load current causes a lot of problems starting from the size of the transistor. What is the size that you have to maintain? And as the size of the transistor goes very large, for example, to the tune of 7,200 devices of unit size that you have to have. Now you will look at challenges like how do you do the layout of this pass transistor, whether you would use a common centered layout, how do you connect the drain connectivity for all these nets as that you have minimum IR drop, or how do you maintain the current delivery is one point. Second, the voltage input that you have the power mesh, right? You will have unique routing congestion and top metal sharing issues. We will be looking at that. Then the inherent device capacitance, so it has a significant value and it contributes to the loop stability. It ensures that the pole shift will move to the leftwards. That means your bandwidth of the LDO will reduce. Further, you have the CGD cap, and this CGD cap also will introduce a secondary pole, and this pole also moves leftwards, and also it provides some amount of stability. So it has got, we will look at the intuition how it is. Further, we will look at the output power mesh where you will have the output voltage delivery and also among the current delivery that you are going to look at. You will have a reduced MIM cap value. You will have a lot of routing congestion because you will have routing congestion both at the input and at the output, and you will have to clearly distribute and partition the input nodes and the output nodes and their various locations, and you will have to understand that the top metal layer will have sharing issues. So along with this, you will have important points to be focused on the gate connectivity. You should ensure that the resistance is minimal because you'll have long poly tracks when you're connecting, or when you have a metal connectivity, you will have to ensure that there's low resistance. The capacitance that is present needs to be optimized such that it is not impacting. If there are any antenna effects, because having a large poly and you will have large metal routes, so potential antenna problems have to be looked at. There is going to be noise at the gate because there is large gate size. Gate resistance is also there, so the noise contributing will be there. And you have to understand that a lot of poly via metal stacks will be available in the gate size. Since you have 7,200 devices, they need to be connected to the metal. The gate to metal connectivity will be there. So these are some of the important design challenges, and we will address at the end of this talk. You will see the summary of all the problems being addressed with this. An important point when we go into while looking an LDO, since it is a feedback mechanism, is what is the loop gain. And the loop gain stability plays a very important role in providing the right kind of LDO output current and the regulation that we will look at. So what are the factors contributing the loop gain? You will have the gain of the error amplifier and the pole contribution of the resistor of the output resistance and the load cap of the error amplifier, represented here by REA and CEA. Next, we will have the pole contribution of CGS cap. Then we will have the gain of the transistor device or the pass transistor, which is the GMP and ROP. And then it will come in a feedback factor. Since it is a unity feedback, we will not have a major contribution, but we will look at what are the possible zeros that could enter. The dominant poles are the output of the error amplifier, which is GM, the CEA and REA, which will fall one of the poles. The second pole is formed at the output, which is a combination of ROP, which is the output resistance of the LDO pass transistor, and the cumulative effect of the CGD and the CL cap, which is seen at this particular node. So these are going to be the two nodes. Now, how does the loop gain impact? The amount of the loop gain that will be there will directly correspond to what is the variation that is seen at the output load due to the amount of current drawn at this node. Also, what is the noise coming on the power line supply. These two are quantified as line regulation and load regulation. So we'll look at how this has contributed in the later part of this presentation. Now we will look at some of the details of the layout challenges. Before we go into the layout challenges, we can give a quick overview of how the layout of the LDO has been laid out. Here we have the driver circuit present predominantly in the center, which will take care of the current delivery and also the load current. If you look at the driver on the left hand side, all the left hand side is covered with the power supply decap, and the power supply decap can be partitioned into the output node and the input node. So the power supply decap for this would be the regulated output could be on the bottom side, and the input node decap could be the forward side. Now, if you look at, there are the bias generation circuits which are present to drive the amplifier, and the voltage references are present here. A discharge circuit is present as a circuit protection mechanism to ensure that if any residual charge present on the LDO cap, output cap, or on the LDO drivers will be discharged when the LDO is not in use. So a discharge circuit is present. And the feedback circuit begins here, where the resistive feedback and the error amplifier is taken from in this portion, in this blue portion, where the negative circuit is present, and the input for that is given through the voltage reference along with a low pass filter, which is present to ensure that the perturbations present in the circuit which get picked up from the feedback point are captured here. So a low pass filter and the VREF circuit block are present here, and this is the entire layout. Now, if you look at the layout way, they are designed in such a way that the feedback is voltage reference input is coming from the far right, and it enters into the negative feedback loop with the error amplifier into it. The output of the error amplifier drives the driver, and the driver output is given with the voltage supply decap present over here, and the output is given out through on the south side. From the north side of this circuit, you will see the power supply input coming into the LDO, which is the LDO input there. Now we will look at one of the challenges, which was the power mesh design. So the power mesh is present at both the LDO input and at the LDO output. When I say power mesh, I am hinting to this connectivity present on the PMOS transistor, both on the LDO output side and the LDO input side and the LDO output side. So here you have the regulated output, and here you have the LDO input, and where the power supply is connected. So the power mesh is for the metal connectivity at the power supply and the metal connectivity at the drain. So we will be looking at these two portions where the power mesh is used. So how is the power mesh designed? On the in the figures A, B, and C, you will see the top view of how the power mesh is designed. You can see they are designed as unit cells, and they are staggered in an example of 4 cross 4 here, and it is fit into how the system needs it at that particular level. The power mesh is again stacked up with metal layers, and we see the metal layers are orthogonally placed, where one metal, if it is looking into the circuit, that is coming out of the circuit, then you will have the other metal in orthogonal in the 90 degrees placed. So if the one metal is coming this way, the other metal is going out this way. In this case, we will the importance is given to how the via, that is to be present between the two metal stacks, and to ensure that the power delivery happens right from top to bottom. This is crucial because to reduce the amount of IR drop that is present, and to ensure clear delivery of current data. Now, important is the top metal layer have higher current density. That's why you would see they are fatter in size or thicker in size, and they have a lower unit metal resistance. The intermetal capacitance, the capacitance that can be formed, or the stray capacitance which can come up between these two metals, can be used to hold the current values and voltages, and this can act in power delivery. The parasitic can be reused as a power delivery aspect, and very careful via placement is to be taken care of to ensure power delivery from top metal layer to bottom in the power supply, and bottom to top. So both vias presence has to be taken care of for input and output power deliveries. An important factor comes in when you are delivering a large amount of current across a device size, and that comes into picture because we have 7,200 fingers of the input. Now, when you have this kind of device size, there is going to be large amount of voltage drop across this transistor. So, to avoid the max voltage drop, we have to take care of something called EOS, which is the electrical overstress. We need to ensure that the field that is present across the drain and source does not stress the device into higher limits. So to avoid that limits, we have to protect the supply. So what is the method we follow? Large VSD can damage the device and reduce the lifetime of the device. So the method that we follow is, we will distribute the entire VSD across two devices. That way your stress on the first device is minimal, and rest of the device can act as a protection, as well as to ensure that the flow is taken care of, current flow is taken care of. So what we do is, we add a cascode device, a second cascode device of the same size, that ensures the same amount of current that flows, and the VSD is now broken down into two devices. That way the stress on each of the devices is lesser, and this allows for even supply changes. So some amount of supply variation that you would see would get protected by this cascode device, and the variation would be lesser. This would include the load regulation that will happen, and also since you are going to have a higher gain because of this cascode, you will see better regulation, also protection from the line regulation that you see in the input. Now, there is an impact that you would see because of this cascode. What is that? We will see an extra set of capacitance that is going to come. But now what we would see is the capacitance would now be transferred. The load capacitance would now be transferred to a CGD at this particular node from here. Without this device, this would be the initial place where the output node would be present. Now that output node is transferred to a lower place where the output node is present here, and it is from here that the output is drawn. The compensation caps that are present here would help in maintaining this particular device gain and your loop stability, and this will also impact to show what is the CGS that will come here, and what is the pole or the far outside secondary poles that are coming. They would get compensated by the presence of these CGD and CGS of the cascode device present here. Now let us look at the results on how what are the proposals that we gave, and how the results solved the challenges that we had in the device. So first thing we had to take care was effective error amplifier design. So the error amplifier had to be designed in such a way that the it responds without any difficulty to the output change. So the current load that would come, that would get pulled from a 0 to 230 milliampere that was present here, that output load current should be your error amplifier should be able to support. Now in this graph we see that the error amplifier is able to support a range even from 1 milliampere to 200 milliampere, and the phase error also is given here. So what do we see as the gain margin, phase margin? The gain margin is we see as 5 dB between these two load currents, which is manageable and does not destroy, since we have the maximum load maximum gain that we see at the DC to be greater than 50 dB. And the phase margin that we observe beyond the operational frequency of 1 megahertz, you see a phase margin of 10 degrees. And this phase margin is around the 60-degree phase. So from 60 to 50 degrees of phase margin is what we get. And this allows good error amplifier response at the frequency level, and also as transient current load level, where tracking can happen and better feedback can happen. Next, we will stepping on from the load current. Now we will look at how the load is enabled. In this particular graph, we show that the LDO begins when we have an LDO load enable signal being asserted, and once this is asserted, the entire signal begins operating. As the load LDO goes higher, we need some amount of transient load current, or DC quiescent load current, that needs to be present, and this quiescent load current is taken care of in the leaker portion. So we have a leaker circuit which gives a finite amount of current to be present, and to ensure that the loop stability is maintained and it is not broken. So leaker is enabled, and this leaker enabled is in the microampere range. So some amount of current will go to ensure that the loop is stable and we are able to function. After the leaker gets disabled or deasserted when the operational circuits start to ping. In this case, we will have the uh, uh, main delay line in the operation circuit for the clocking. So when the delay line gets enabled, the leaker gets enabled, which disabled, and this allows the stability to be maintained. So it is a make before break circuit. So first we will make or enable the MDLL, and only then disable the leaker circuit. Along with that, here we show a sample read, write, read condition, in which we take the cycle to how the read enable happens, where for one of the data reads of close to 175 milliampere, we are able to get the data read current. And for that particular data rate, we see that the amount of switching that happens is minimal, and this ensures that the load regulation is very good. And when we switch from 175 to 140, we have this transition. Again, there is minimal load regulation, or minimal load change, and showing effective good load regulation. Again, when you come back, we do not see that effect. We only see that effect when the LDO is disabled, and as the LDO is disabled, the output load voltage slowly discharges, and we have the discharge circuitry which we mentioned, through which the discharge happens, and the current in the load circuitry is brought down to almost zero or to the leaker levels. So when the LDO is enabled, only then we will need the leaker to be enabled. When the LDO is not enabled, we can turn off the leaker condition. So this way we will maintain the loop stability of the system. This is a quick in detail discussion of how you maintain the load ripple. We see that when we apply a supply voltage of 1.1 volt and 100 millivolt ripple at 100 megahertz. So the frequency here is 100 megahertz, and the ripple that you see here is about 100 millivolt. If we look at the total output regulated voltage, which is the graph here in blue, so the regulated output for a 200 milliampere load shows a ripple of only 14 millivolt at the highest. So this shows that the output is significantly well understood, and the regulator output is set at 166 millivolt, which is close to 140 millivolt of dropout voltage that we see from the power supply, a 1.1 volt input to 966 volt or 140 millivolt dropout, and this is the amount of ripple that we see at 14.7 millivolt, which supports our really very good line regulation that we see on the power supply. At the load regulation here, like we showed in the last two slides, the load regulation here is shown that only about 3 millivolt of load regulation is observed for various input supplies, and as we transition the load supply from 34 milliampere here to 170 milliampere for the maximum load supply. So this is before the MDL can be enabled. This is after the read cycle in this particular test case. And we see that the rise time is about 13.6 milliampere in 10 nanoseconds, per nanosecond, and this rise time is defined at 10 nanoseconds. So within a 10 nanosecond period, a 3 millivolt disturbance is a sign of a good load regulation in the circuit, and this is attributed to having a good PS, power supply rejection ratio, also having the good gain in the system, and also the presence of the cascode device, which further enhances the gain in the system. So all these three contribute to a better load regulation in our design. So quick comparison, we did not have too many circuits showing uh, maximum load current range of 0 to 200 or 0 to 100. So we had one capacitance, one reference that we have taken. And if you look at our load range, though we are in the 0 to 100 range comparison for the 65 nanometer, since this was a 7 nanometer work, we are using the similar figure of merit and showing that it is functional at 230 milliampere also. And if you look at the input voltages and the output voltage and the analog architecture, they are similar in comparison. Now, the focus points that we would like to bring out is to show that the PSRR that we have, the power supply rejection ratio, is 32 dB at 51 megahertz, which is 5 times more and 5 dB higher than the comparison voltage. The delta V in millivolts that we see per load step, we see only a 3 millivolt increase for a load step of 135 milliampere, whereas this shows a 228 millivolt for 100 milliampere. So taking into factor the change in the design technology, we can easily say that if not for 10x, they can easily be a 5x betterment that we see in the load regulation that we see. The settling time is also 10x better, that we see that settling time happens in under 120 nanosecond that we see, whereas for this particular work, reference was seen in 2000 nanosecond was taken, or less than 2 microsecond was given as a settling time. So this allows for fast read write times where you are able to switch, and also ensure that with the settling time you are able to reduce the latency of data transfer also coming from the power supply operation. So this is a reference work that is taken and given here. So in summary, the design challenges for current delivery were highlighted. Specific interest was shown on how the large device size was posing a challenge. So we understood what was the device cap, inherent cap, how it could contribute, what were the layout methods we had to follow to ensure that the large transistor size is going to be a benefit. We talked about what is the power delivery methods and the device protection methods using the power grid that we showed for device, and also how the cascade device can be used for device protection. The gate capacitance that was involved and how its loop stability was better, and we also showed results on how we got 5x better line and load regulation in this presentation. With this, we would like to summarize and show that these are the reference circuits that we have used for the design comparison. Thank you very much. I'll open for questions now.